Hey guys, welcome to MACM 101, Discrete Mathematics, Tutorial 1. My name is Jiawen. I'm one of the TAs this term, and I'm also the host of this tutorial today. During this term, I and my colleague Interpartive will run tutorial each week. In addition, we have live question and answer sessions for each tutorial. You should already receive the email from the instructor about the tutorial. So, each week, we will post the tutorial question in advance on Canvas, and you are encouraged to solve them by yourselves first. After that, you can watch the pre-recorded tutorial videos. We will provide a step-by-step explanation for every single question. But remember that there could be many ways to solve the questions. What we provide is just the guide. We are not going to restrict how you solve these questions. If you still feel confused after watching the tutorial videos, feel free to join the live question and answer session. We will help you with any difficulties. Honestly, it's the first time, not only for me, but also for our teaching team, to deliver the course remotely. So we may adjust some methods along this term, but we are trying our best to help you. Hope you enjoyed this course. Thanks.
All right, let's go straight to the questions. So the first question, state the converse, contrapositive, and inverse of each of these implications. When you ask to play with an implication, you need to find the hypothesis and the conclusion. Let's take a look at the first one together. If it snows today, I will ski tomorrow. What's the hypothesis and what's the conclusion? The first statement is, this one is simple. If P, Q, clouds. So the hypothesis is snows today, and the conclusion is ski tomorrow. So then the question asks you to find the converse, contrapositive, and inverse. So first, let's find the converse. Assume this statement is if P, then Q, which in the if we write in the propositional logic is P implies Q, and the converse just swap the hypothesis and conclusion. So we have converse is Q implies P, which should be if I will ski tomorrow, then it snows today. And then the contrapositive. If the statement is P implies Q, the contrapositive should be the not Q implies not P. So what's the contrapositive? It must be if I won't ski tomorrow, then it doesn't snow today, right? And what about inverse? Inverse is not P implies not Q. So what we have is if it doesn't snow today, I won't ski tomorrow. All right, let's move to the second one. I come to class whenever there is going to be a quiz. This one is a little bit complicated, but similarly, we we need to find the hypothesis and conclusion first. So, what is P and what is Q in this case? You guys should see the same statement in the lecture that I used whenever. So let me simplify the statement first. The second one, I can do class whenever there's going to be a quiz. So simplified, it will be if there is going to be a quiz, then I come to class. Right? We simplify the statement to a very simple implication. But they may have a quiz or may not. We don't know. But if there is going to be a quiz, I will come to class. Right? So let's play with the simplified statement. What's the converse of this statement? Alright, or maybe we should indicate the hypothesis and conclusion first. I think is there is going to be a quiz is hypothesis, and I come to class as a conclusion. So converse first. Similarly, converse is just P implies Q. Q implies P. Sorry about that. Q implies P. So we have if I come to class, there is going to be a quiz. Right? The contrapositive should be not Q implies not P. So we have if I don't come to class, then there is not going to be a quiz. Okay, inverse now. Inverse. What's the statement again? If there is going to be a quiz, then I come to class. So inverse is just not P implies not Q. So the not P should be if there is not going to be a quiz, and not Q should be then I don't come to class. Right? Not P implies not Q. So at this point, we have finished the first two. Let's have a look at the third one. This statement is fairly complicated than the above two. This one is a compound statement, and there is a logic connective and. But don't worry about that. It's just the same way, right? We first simplify the statement. So what's the statement? A positive integer is a prime only if it has no divisor other than 1 or itself. So the third one, I tried to simplify it first. If a positive integer has no divisors other than 1 and itself, then it is a prime. Right? After we simplify that, we need to find the premise and the logic connected. So here, a positive integer has no divisor other than 1 is the first hypothesis, the first premise. And the second, positive integer has no divisor other than itself, should be the second one. Then the conclusion, or we call the third premise, is it's a prime. We can write it as R. So we have 1, 2, 3, P, Q, R. Then we write this statement into the propositional logic. It's just P and Q implies R, because here is the logic connective. So so let's write the converse about this statement. When you write the converse or contrapositive or inverse of any compound statement, you can treat the compound part as a whole part. And then we have R implies M, which is just R implies P and Q, right? So we write the statement in English. It's just if a positive integer is a prime, then it has no divisor other than 1, and it has no divisor other than itself. It's not that difficult, right? And then we want to write the contrapositive. Contra here. Contrapositive is not R implies not P and Q. And we want to put the negation inside the, so we have the not R implies not P or not Q. Here the conjunction becomes the disjunction because we put negation, so we need to change it to the opposite. So we have the 8 it a positive integer. It's not a prime. Then it has divisor other than 1, or it has divisors other than itself. Right? Makes sense, right? If a positive integer is not prime, then it has divisor other than 1 or other than itself. Right? And the last one is inverse. Inverse is not P implies not Q, right? In this case, just not P and Q implies not R. So we have not P or not Q implies not R. So we have if a positive integer has divisor other than 1, or it has divisors other than itself, it is not a prime. And it's not that difficult than we expect, right? Let's recall what I have said. So when you ask to write the converse, contrapositive, or inverse of any implication, you need to simplify the statement like this. You have whenever you just simplify it in using the if then clause, and after that you find all the premise. If it's a compound statement, we need to find all the logic connectives. Then you write the converse, contrapositive. If there is some negation or something, if the negation used with a conjunction or disjunction, you have to remember change the conjunction or disjunction to the opposite tab. That's it. Okay, let's move to the second question. Question 2. Then question 2 asks you to extract this system specifications using propositional logic. Construct the truth table for the compound statement. Let's see the statement. Access is granted whenever the user has paid the subscription fee and enters a valid password. When you ask to express the system specification in propositional logic, you first have to determine the propositions. So we suppose P is the user has paid the subscription fee, and Q is the user enters a valid password, and R is access is granted. Then again, we want to simplify the statement. So we have again, I'll find the whenever. So as I just said, A whenever B can just be write as if B then A. Then we have the if the user have paid the subscription fee and enters a valid password, then access is granted. So write the statement in propositional logic. The user had paid the subscription fee is P, and enter a valid password is Q, and access is grant is R. So we have and when you ask to write English language system specification into a propositional logic, after you find the hypothesis and conclusion, you need to find the logic connectives. So generally we have the P and Q implies R. Yeah, this one is a logic. This one is a propositional logic. And the question asks you to construct the truth table. So let's do that. We have 3 propositions, so then we need 8 rows. Just P, Q, R, P and Q. That's a P, Q. Oh, sorry. Q, R, P and Q. P and Q implies R. So we have false, 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 true, false, true, false, false, true, true. 1 0 0 1 0 1 1 1 0 1 1 1 1 2 3 4 5 6 8 rows, right? Then what next? We need a P and Q. Let's generate the truth table of P and Q. As you learned in class, the logic connective AND is if there is one false, then the whole statement will be false. right? So we have false false is false, false true is false, true false is false, and true true is true, right? Then what we have here is just false false, false false, false false, false false, false true, true false, false true, true true. Right. Then we need to find the truth table of the implication. Let's generate one. P Q, P implies Q. So if the hypothesis is false and the conclusion is false, then the P implies Q will be true. But if the conclusion is true, it will always be true. But if the hypothesis is true, but the conclusion is false, then the implication will be false. So what we have here is P and Q implies R. P and Q here, R here. So false implies false will be true. False implies true will be true, because if the conclusion is true, then the whole statement will be true. So we have true, true, true here. And here the hypothesis is false. The conclusion is true. Then conclusion is false. Then the whole statement will be true. Same way. But here, look here, the hypothesis is true, but the statement is false. So we have false here. Right? Then we have the propositional logic and truth table. We done? Right? Here's propositional logic and the truth table. Great. Let's move to the question 3. The question 3 asks you, are these system specifications consistent? Okay. There is a statement in the textbook says that system specifications should be consistent. That is, they should not contain conflict requirement that could be used to derive a contradiction. Which means if there is a contradiction, then the specification is not consistent. So what about this one? The system is in multi-user state if and only if it is in operating norm, and if and only if it is operating normally. If system is operating normally, the kernel is functioning. The kernel is not functioning, or the system is in interrupt mode. If the system is not in multi-user state, then it is in interrupt mode. The system is not in interrupt mode. Oh gosh, so long. So first we analyze the system specification. When you want to analyze any specification, you want to find the premise first and the logic connective. So we want to rewrite this specification in a short form. So have a look. The system is in multi-user state and it's operating normally. We call it N. And operating normally. The kernel we call K. The kernel is not functioning. Kernel functioning. K. Functional system is interrupt mode. If the system is not in multi-user, then it is in interrupt mode. This is not in interrupt. All right, we have found all the premise. We have I, N, K, I, right? Then we want to find the logic connectives. We have if and only if. We have not, or we have the not. This is not here, right? Then we can rewrite it in a short form. We have back condition, if and only if n, we have n implies k, we have not k or I, we have not implies I, and we have not I. So if this system specification is consistent, each statement must be true, right? And so first, if we want the not I statement be true, then I must be false, right? This negation I. So I must be false. Where's I? We have I here and I here. So not k or I, if f is false, then the not k must be true. Then k must be false, right? So what do we have next? We have not I implies I. We know I is false, and we know the truth table of the implication. If something implies false, if something implies false, we want the true, then the not I must be false, right? Because false implies false is false. Oh, sorry, false implies false is true. Sorry about that. And then we know not M is false, then M is true. We have M is true here and true here. Let me have a look of the if and only if n. If we want the statement M if and only if n to be true, then both M and n should be true. It's just a simple logic. So then we have n is true. We have n here. And then we have a look at n implies k. As we know, if we want the final result of the implication is true, and we know the hypothesis is true, then the k must be true, because true implies false is false. So the k must be true. However, we know where the above, we know k must be false, and here we know k must be true. Then here is a contradiction, right? Because by the analyze, we first find k must be false, then we find k must be true, then it's a contradiction. And as I just said, if the system specification has any contradiction, then it is not consistent, right? Then we're done, right? Question 4 asks you to draw the truth tables for the following formulas. Okay, the first one, we have 2 premises, so we need 4 rows, right? So draw the table. P, Q, P implies Q, Q implies P, final statement. So we have P, Q here, P implies Q here, and Q implies P here. Then we have P implies Q implies Q implies P. Alright. So false, 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 true, true, false, true, true. When you ask to construct the truth tables during the exam, be careful about it. Ask you to use the 0, 1, or use the TF, or use the true, false. Okay, careful of that. So if both P and Q are 0, so by implication, by the truth table of implication, we know P implies Q is true, right? Let's draw the implication truth table. False implies false, it's true. False implies true, it's true. True implies false is false. Sorry. True implies false is false. And true implies true is true. Then what do we have here? So it's just true, false implies true is true, true implies false is false, true implies true is true. Then we need the Q implies P. What the Q implies P? Q here, P here. False implies false is true, true implies false is false. And we have true, true here. Then we need the P implies Q implies P. So we need the 1 implies 1. The true implies true is true. True implies false is false. False implies true is true. And true implies true is true. Right? Very simple. It's just the truth table. And not hard. And the second one. Oh, the questions with the stars is a bonus question. It could be a little bit complicated. It could be a little bit difficult, but not really. Not very. Then the second one. Second one is P by condition. P if and only if Q. XOR. This one is XOR. And negation P, not P, if and only if Q. So same thing. Need 1 row for P, 1 row for Q. P infinite Q. Right. So we have P, Q. P if and only if Q, not P if and only if Q. So P if and only if Q, XOR, not P if and only if Q. So same way here. If and only if. If both sides same, then the final statement will be true, which means if P and Q both be 0 or both be 1, then P if and only if Q will be true. The false is true, true is true. Otherwise, it will be false. And okay, I think we need one column for the not P, right? P, not P, just negate that. Very simple, very simple. Then we need the not P by condition Q. So not P here, Q here. Same way if it's true, therefore false, that will be true. If they are different or they opposite, they are false. Right. Then we need this column and this column. Is XOR. Let me draw the truth table for you. P Q P XOR Q 0 0 1 1 0 1 1. The truth table for the XOR is for the XOR gate. If both sides are the same, then the output will be false. If the both input is opposite, then the output should be true, which means here we have false, false, true, true, then P XOR Q will be false. But if the both inputs are different, then the output should be true, which means so 1 0 different, so we have true. 0 1 different, true. 0 1 different, true. 1 0 different, true. So this statement will be true, 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 true. Right? Cool. And third one is P implies Q and not P implies Q. Okay. Oh, sorry about that. The third one, same thing, same way. Truth table P Q. Not P. P implies Q. Not P implies Q. I'm sorry. And P implies Q and not P implies Q. Okay, so we have 0 0 0 1 1 0 1 1. So first they negate P 1 1 0 0, right? After that we want P implies Q. P implies Q. We know false implies false will be true. False implies true will be true. And true implies false will be false. And true implies true will be true. It's just 1 1 0 1. And we want the not P implies Q. Not P implies Q. We need this column and this column. Not P implies Q. True implies false will be false. True implies true will be true. False implies false will be true. False implies true will be true. Then the final statement. We need this two, right? We need this two. So 1 and 0. The logic connecting with and, if there is any false, then the whole statement will be false. So false, false, so it will be false, and this one will be false, and otherwise they will be true. All right. Both the question 5 and 6 are logical puzzles. Let's see the question 5 first. It's a story about knight and knaves. So there are two tribes living on the island of knights and knaves. Knights and knaves. Let's always tell truth, and the knaves always lie. You encounter two people A and B. What are A and B if A says B is a knight, and B says the two of us are opposite types? When you try to solve a logic puzzle, you need to assume something. You need to assume something first. So let's say, let's assume A is a knight. If because knight always tell truth, so B B must be a knight as well, right? Because A says B is knight and knight of tell truth. However, B says the two of us are opposite types. So if B is the knight, he never lie. So there is a contradiction, right? Contradiction again. There is a contradiction. Thus, A must be a knave. And then, because knave always lie, so A says B is knight, right? So A says B is knight, then B is a knave, right? Because knave always lie. So A says B is a knight, so B is knave. Is that clearly? So when you try to solve a logic puzzle, you just assume something. If there is a contradiction, then the assumption is false. It's incorrect. And if the the conclusion will be the opposite. And the 6, nothing special, just assume again. Assume A is a knight. Assume A is knight. Then B is also knight, because knight always tell truth, and A says the two of us are both knight. If A is knight, then B is knight, right? So far, B is knight. And B says, what B says? B says A is knave. B says A is knave. But by our assumption, A is knight, but B says A is a knave. Here is a contradiction. Yep, we found a contradiction. Then the assumption is false. The assumption is incorrect. So so A must be knave. A must be knave. And then, because A is knave, I don't care about what A says, because knave always lie. So what he says is just a lie, right? So we care about what B says. B says A is a knave. B says A is knave, and our assumption is A is a knave, right? Then B must be a knight, because knight always tell truth. So B says A is a knave, and our assumption is A is knave, right? Cool. The second last question asks us to use truth tables to verify the absorption law. I think you guys must learn the absorption law in lecture 3 or 4. Yeah, I'm not sure, but it must be in 3 or 4. So let me write it for you. What's the absorption law? Is P and P or Q, logic equivalent P, and P or P and Q, logic equivalent P. So it asks us to use truth tables. So simply we construct a truth table. We need for P, Q, P. Sorry, P or Q, P and P or Q. Similarly, we need false, 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 true, true, false, true, true. And here is disjunction, right? Logic disjunction. If there is true on the other side, then the output should be true, right? Here is no true or true, so the false, true, true, true. And so we have this column and this column. So here is a conjunction, right? Conjunction is that if there is a false on other side, then the output is false. So we have false, false, true, true. Where's P? Oh, P. Write it again. If we compare this row, these two, compare these two columns are identical. So these two propositions are equivalent. So we have to, the first one done. We need the second one. False, 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 true, true, false, true, true. It's conjunction, so we want to looking for the true, right? Oh, sorry, we want to looking for the false. If there is any false, then output should be false. The false, 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 true. And we have the N, Q, and P. Where's the disjunction? So we are looking for the true, right? So true, true, then we have true, true, but the false, false. Where's P? Write the P again, 0, 0, 1, 1. Compare this row, this column and this column. Both columns are identical, right? So same thing, then these two propositions are equivalent. So we use the truth table, verify the absorption law. Done. The final question asks you to show the statement is a tautology. Use equivalence. To show the statement is tautology, we have to show the statement is true regardless the value of P and Q. As you have learned in lecture 4, I think, there's a theorem that an implication can be right using only conjunction, disjunction, and negation. We have to use logic equivalence to eliminate all the implication. So first, by implication equivalence, we have this statement is logic equivalent to the not P implies Q and Q implies R or P implies R. And next step, we want to put the negation inside. So we have not P implies Q or Q implies R. We change this one, we change the conjunction to disjunction because we put the negation inside. Oh, sorry, here negation here. Or P implies R. Then we have we want to eliminate the implication inside. So we have not P or Q or not Q or R, not P or R. Next step, same thing. Yeah, same way we want to put the negation inside, then we can eliminate the negation here, so we have P or Q. Sorry about that. P and not Q, or Q and not R, or not P or R, because the logic connective are all disjunction, so you are free to change the position of any statement. So we have the P and not Q, or not P or Q and not R, or R. So here you need to use the absorption law to put the not P and R inside into this one and this one. So by the absorption law, we have not P or P and not P or not Q, or R or Q and R or not R. Here, R and R or not R is true by the inverse law, or the what's it called is the law of contradiction. Here, same thing, is true by the inverse law. Then we have the not P or not Q or R or Q, right? And we need to combine the not P, we combine the not Q and Q together, then or P or R. And again, by the inverse law, yep, this one will be true. So as we know, if there is a true in a series of disjunction, then the whole statement will be true. Here is disjunction, then the whole statement will be true. So this logic is true. Then we finish the proof. We have shown the statement is tautology, because whenever the P or Q, whatever the P is 1 or Q is 1, the final statement, final output will be true. So this statement is tautology. Yep, that's all the content I plan to cover in tutorial 1. If you have any question, please feel free to join our live question and answer session, or raise any question on Canvas. It's under the discussion tab. We will create one discussion per tutorial. Yep, that's it. Stay safe, guys. Bye. Thanks.